All right. Welcome, everybody, to today's Anti-cast brought to you by Antisyphon Training with very affordable, high quality training for information security. We got Hal and John with us today. They're going to talk about monitoring with eBPF.
I know it's a tongue twister.
I know I have no idea what those letters stand for, which is why I'm excited for today's webcast. If you have any questions at any time, feel free to ask here inside Zoom, or you can join us on Discord. Discord's great because you get a chance to like hang out with the other people and talk to the other people, and the other people can help answer your questions as well. Hal, you need anything before we get started?
No, I've got rhythm, and who could ask for anything more?
Fantastic. All right, John and Hal, it's all yours. I'll be here in case you need anything. So if you do need anything, just ask and I'll be right here.
Right on. Thanks, Jason. Hey, look, it's me, Hal Pomeranz, sort of the Unix talking head. I've been doing Unix for a really, really long time. Really long time. These days, I'm bringing my Unix knowledge as an independent consultant, doing a lot of incident response, expert witness work. You've probably at least seen the advertisements for some of my Antisyphon training. You can go to the Antisyphon calendar. We've got training coming up in July. That's my contact info if you have any questions after the course is over. Let's get right down to it. Okay, so look, we're talking about like logging and monitoring here, right? So historically, the problem with logging in Unix has been that it's discretionary. And what that means is that it's left up to the developers to put logging into their application. And what they choose to log and when they choose to log it is, entirely up to them. And so the problem, there's a whole bunch of problems with that, right? One is that, if you've ever done any sort of project with, kind of log aggregation and analysis from Unix and Linux systems, one problem is that like the logs are all over the place and they don't follow a consistent format and they're a big pain to deal with. But the other big problem, of course, is that anything malicious happening on the system is almost guaranteed not to be logged because, the bad people and their malware aren't going to, be logging useful information for you. And so what you want is mandatory logging, something that happens at the OS level and is inescapable from userland. And historically, in the Linux universe, that has happened through Audit D. And we'll talk a little bit about Audit D as a lead-in. And then recently, sort of starting in the late version 3 kernels, but really happening in the Linux version 4 kernel, has been this new thing called eBPF. And we'll talk a little bit about where that came from and how that happens for you. Okay, so let's start with Auditing. So back in the day, right, there's this desire on the part of many organizations to have mandatory logging in the operating systems. And this was driven actually a lot by the US DoD. And so the idea was that, hey, let's have something that can monitor what's going on in the operating system at the system call level. And the initial way to do that in Linux was with Audit D. And basically, it's a kernel monitoring system where you can effectively monitor every single system call that's happening in the OS. The basic functionality out of the box that you see implemented on Red Hat systems is it'll log user logins, privilege escalation, system reboots, scheduled tasks, and all of the insanity that's happening with SE Linux. Anything further than that, you have to configure it, right? And you can configure Audit D to monitor specific files or directories full of files. Like, for example, you might have it monitor things like your password, your shadow, your group, and your sudoers files for people making changes that might give them extra privilege and things like that. But fundamentally, what's going on under the hood, and which you can use, is you can monitor any system call you want. So you want to monitor every single process execution. Cool. Then you monitor the exec VE system call, and you can log every single process execution. You want to monitor, privilege escalations. Well, set UID is it's a system call, and you can monitor for that. And so ultimately, you can actually turn this thing into a keystroke monitor for Linux, which is a lot of fun, and I like to show my students how to do that. But basically, the thing is, it's this toolkit that allows you to monitor anything on the system. The problem is, if you turn on too much monitoring, you get some significant performance degradation. So you have to be kind of careful about what you monitor. The other big problem with Auditing historically is the output format. Basically, here you go, right? So this is raw Auditing output for a single event, which would be somebody opening the Etsy password file. Now, I mean, there's a lot of good information here. I mean, don't get me wrong, right? You can see, look, this was the user ad program. It was started by user ID 0, which is the root user. But the actual user ID, the user that the person logged in as, is user ID 1000. You can see what directory they were in when they ran the program. Up here, this hex encoded blob of nonsense is the actual command line that they ran, hex encoded. You can even tag this stuff with your own user-defined keys, for searching and things like that. So I'm not saying this isn't useful, but there's a whole bunch of distraction and noise in here, right? Like, you don't get somebody like me helpfully bolding the important fields in all of this. And so, you can monitor lots of useful stuff, but you're sad because there's just so much stuff blasting you in the face with this stuff that it's hard to pick out the things that you want, right? You want the little tractor down there, but somebody's got a hose in your face and you can't find the tractor, and you are sad. Okay, so Auditing for a long time was basically what you had in Linux, and there were projects that tried to post-process the Auditing data and do useful things with it, but it was still kind of an expert level system. And so then some of you may have started hearing about this whole BPF thing, right? So what is BPF? So BPF stands for Berkeley Packet Filter. You're like, Berkeley Packet Filter? Wait, isn't that like TCP dump and libpcap and all that stuff? Yes, exactly. So in the beginning, right, there was TCP dump. And TCP dump was cool and performant because it did this neat little trick of putting a very simple VM into kernel space. It was this tiny little simplistic VM that ran this specialized bytecode, only had a couple of registers. But what it could do was it could sit there and watch packets coming in through the network stack and filter those packets based on filters that you created with the TCP dump program in userland, just-in-time compiling, and ran the filters ran on this little virtual machine inside of the kernel, which was cool because it meant that your user space program didn't have to copy every single packet out of kernel space to filter it, right? The filtering happened in the kernel, and then your user space program, TCP dump, only got the packets that it was interested in. And this was a huge, performance increase. And it actually allowed, TCP dump to kind of do what was needed to be done. I mean, there were other network monitoring tools at the time, but they always run into significant performance issues as network speeds ramped up. So this was really cool. I mean, but remember, I mean, this is like early to mid 90s technology, right? And it didn't age so well. I mean, first off, it was a 32-bit VM. It only had a couple of registers, so you were limited in what you could do with it. And so, there was this discussion about, well, don't we need to update this for modern times? And, while we're at it, if we can already have something in the kernel that can filter packets and decide, which packets the user wants to see, couldn't we also filter packets and use it as a firewall, right? And so the initial idea there was to create something that would replace the net filter code, IP tables, in the Linux kernel, and replace it with BPF as a more performant solution. And then the thought was, well, wait a minute. I mean, if we're already hooking the system calls in the kernel around the network stack, why stop there, right? Why not create something that's a little more generalized and actually allow people to filter on pretty much any trace point in the Linux kernel? And that's what led to eBPF, extended BPF. And so it's not about packet filtering anymore specifically. It's about filtering kernel system calls in general. And so the eBPF project is now at great pains to tell you that eBPF doesn't actually stand for anything anymore. So it used to be BPF, the Berkeley packet filter, and then it was the extended Berkeley packet filter, and now it's just eBPF. And so boom, right? And so now you have in the Linux kernel this sort of generic virtual machine, which is capable of filtering on really pretty much any system call. And in fact, even if there's not a system call trace point, you can create your own trace points at pretty much arbitrary places in the kernel code if you know what you're doing. So, but of course, because it's more general, we're not just filtering on, packet headers and stuff like that. The filtering language has become so much more complex and descriptive because you need to filter on all sorts of different kinds of events. So somehow, from user land, you've got to get your eBPF, let's call it a filter, right, into the virtual machine that's running down the kernel. And it now goes through multiple steps. So you've got to compile your bytecode, and then it needs to go through a verifier that actually, checks certain conditions, like, is it going to halt? Are you trying to access kernel memory that you shouldn't? Blah, 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 blah. So it's trying to sandbox your code because, you're running in kernel space. Now, is that perfect? Oh, no, far from it. You can go and Google for all kinds of bad eBPF vulnerabilities. In fact, if you look back through my Twitter stream over the last week or so, somebody just showed a privilege escalation using eBPF. So there are definite security implications of running arbitrary code in kernel space. And do I believe we've flushed out all the vulnerabilities? Nope, I do not. But that being said, the things you can do with eBPF are totally cool. So your bytecode goes through a verifier, gets compiled into the language for the virtual machine, and then it hooks whatever system calls you tell it to hook, and it proceeds to send you data. And what data does it send you? Well, it sends you whatever data you want. I mean, this is the cool thing about eBPF. You can define your own data maps and just pass whatever data you want from the system call. And so it's not like Auditing, where basically here's your output format. You get to define exactly what data you're going to pull out of all of this, right? So there's a lot of detail. I'm going to give you a demo of a couple of different tools, but the root of all knowledge is eBPF IO, which you can see down here at the bottom of the slide. Now, I'm just going to be talking about eBPF from the subject of monitoring. But the other thing is that eBPF, they wanted it to be a firewall, right? So they wanted to give it the ability to control whether a packet was allowed or denied. But it turns out in the generic eBPF universe, you can actually decide to allow a syscall or not. Like, are you going to let this program open this file, right? And you can create security policy enforcement using eBPF as well. And there are a number of different products out there that are using that capability to, interdict system processes, networking calls, and things like that. And I'm not going to get into any of that. I'm just going to sort of talk about it from just a pure monitoring perspective. But again, if you want more detail, eBPF IO is the place to start. There's a lot of good information linked off of there. So let me show you a little bit more about how this works in practice. Okay, so somehow we've got to get from an eBPF program expressed in a high-level language to actual, code running in this virtual machine in the kernel, right? And so I want to talk a little bit about, what's going on up here in user land. There's a couple of different ways that people commonly launch these eBPF detectors. One is using BCC, the byte compiler for eBPF. Now, you can invoke BCC directly to create bytecode and then sort of manually load it yourself into the kernel. But what most people do is they wrapper BCC up in an interpreted language like Python, for example. Okay, and so here's a really high level view of kind of what that looks like in Python, right? So you import the appropriate libraries, and then you write eBPF. This is sort of C-like language, right? So you can define data structures, you can define functions that you're going to hook onto various system calls, right? So you write your eBPF code, whatever complexity level you want, and then from the interpreted language, you take that C-like high-level language code and you run it through the BPF, BCC compiler, basically, and then you set various hooks, right? So we're going to set a hook on entry into the exec VE calls, right? So this would be somebody starting a new process, and on the return from the exec VE system calls. On the entry, you get to see the arguments that exec is being called with, i.e. the program name and its arguments. On the way out, you get to see the return code, whether it succeeded or failed. And this line here, which you could easily skip over, it's actually kind of an important but subtle point. In order to make this as transparent and stable as possible, you don't actually name the internal system call in the kernel directly, because that would be brittle, right? If the Linux kernel decides to change its system call interface and you had the hard-coded system call names in there, all your programs would break. So there's this abstraction layer where you say, I want whatever syscall is responsible for exec VE, give me that name, and then I'm going to define my hooks on whatever name was returned there by that. So there is an abstraction layer to make your code portable across multiple versions of the operating system. Now, okay, so that seems sort of complicated and a little abstract. but there are literally dozens of examples of using BCC in Python that you can look at. So one of the names that's going to come up over and over again in all of this is this guy named Brendan Gregg, who some of you may remember from the Solaris days with Trace and all of that. Brendan was one of the performance consultants with Sun for a long time. And he did a bunch of tooling around Trace, but he's now sort of moved over to eBPF. And he's written a bunch of programs which are generally referred to in Linux as the BCC tools. And so, for example, one of his tools is called exec snoop. And it's a Python program very similar to what I have on the slide. And I mean, this is just a very simple program, but what it does is it literally watches every process execution on the system. And then he's got another fun one called Open Snoop, which looks for file opens. And you can actually see, like, oh, there's me running Open Snoop, right? And then Open Snoop is telling me about all these things that are being opened. I mean, I just find this stuff sort of fascinating to look at just from a perspective of how the operating system works, right? But, you know, it's a very simple idea. He's just hooked the exec call, he's hooked the open call, and he's outputting whenever somebody opens a file or executes a program. He's got one for networking. So there's a TCP accept, which will monitor people connecting to your operating system over the network. And, you know, I mean, I bet you didn't expect a program like this to open all of these .h files, but this is Python bringing in all of the different networking libraries when I ran TCP accept, right? So it's just sort of fascinating to me, all the stuff that's happening in Linux that you never knew about. There's also TCP connect, which is outbound connections. So for example, I'm going to open up one more window and then I promise I'll quit. Actually, let me log out of my machine here. So I'm going to SSH back into my virtual machine, right? And you can see, here's the incoming network connection, right, for my virtual machine. And then that started, when I logged in, right, it started a whole bunch of processes. That was my user environment starting up. And of course, that opened up a whole bunch of files. So, okay, so there's my connection coming in. So how about outbound connections? So what I'm going to do, actually, let me get rid of here. Oops. So let me just do like an Nmap scan, right? So Nmap. Oh, I'm going to do a connect scan so you can actually see the outgoing three-way handshakes. And I'll just Nmap myself. And so you can see here in the connect snoop, you can see all of the outgoing connects that Nmap made as a result of that scan. So this is, you know, I mean, just from a baseline monitoring perspective, this is pretty cool. You know, Brendan takes this in a direction of performance tuning, like actually getting in and seeing, like, you know, which calls are taking the longest and things like that. He was, for a long time, working at Netflix, doing performance tuning on their streaming service. He's now at Intel doing performance tuning for their whole hardware line. So, and Brendan's written a book, by the way, on performance tuning with eBPF. By Addison Wesley. It's well worth your time if this is a direction you want to go. So anyway, you get the idea. But if you look at one of these tools, right, they live in user share BCC tools. So like exec snoop. Right? It's just a Python program, like I described, right? You know, import BPF, and then down here, here's the actual BPF program, and you can see, you know, it's just this C-like language where you know call whatever data structures you want and pass them in and out. So I mean, you know, cool, but you know, requires a fair amount of programming expertise. So I mean, you know me, right? I'm all about the command line, right? That's my thing. So what about something that's a little bit more user friendly, right? So, oops. Okay. For command line stuff, there's a tool called BPF Trace. BPF Trace, it's sort of this weird awk-like language for interfacing with the eBPF stuff. So, for example, I mean, you'll recognize some of these constructs from awk. So you can have begin blocks, right? And in the begin block, I'm going to output, let's say, a header for my output. So we'll output, I'll output something like exec snoop, where I'll track process executions, right? So I'm going to output the PID and the executable name, okay? And then I need to hook onto the exec call. So I'm going to trace point syscalls that, no, sorry. Syscalls, sys enter exec BE. All right, and what am I going to do when something happens on that trace point? I'm going to minimize this. The Zoom stuff was getting in my Zoom widget was getting in my way. Okay, so when we hit that trace point, what am I going to do? I'm just going to print out the PID, which is a number, and the executable name, which is a string. And I can access those using this PID symbol, and the executable name is a pointer, right? It's a C-type string. So we need to convert it into an output string. So it's argv file name. Okay, so that's what we're going to print out. Oops. Oh, sorry, not argv. There we go. I'm gonna make something happen in another window here. Right, so there's my ls program. Hold on. Okay. So yeah, if you don't want to like go to the trouble of writing, you know, this whole C-like thing, you can kind of on the fly create these little hooks into various functions. Now, you know, the where did all of this stuff come from? So let me point you. There's a directory here called sys kernel debug tracing events. Okay. And you can see there's a whole bunch of different kinds of events that you can hook onto. I hooked onto a syscall event, okay? And under that directory, wow. I mean, so you can see all of the different Linux syscalls that you can hook onto, right? So I hooked onto sysenter exec.ve, but there's also, so there's sysenter exec.ve, but there's also sysexit exec.ve as well, right? If you want to get the return code. And under each one of these directories, so sysenter exec.ve, there's a file called format, which describes, the various fields that are available. So here's that args file name field that I was stringifying, PID, and so on and so forth. So these files tell you the data that's available, at a given trace point. So these files are your friend when you're learning, what you want to capture. But sometimes, like your performance tuning, right? I mean, so sometimes the answer is like, how long does something take? Well, there's no data structure that tells you that. You have to track when the entry happens, when the exit happens, and then subtract, right, to get time. Or if you want to find out the parent process ID of a process, you have to hook the fork and the exec, right, to see which process is starting which child process. So in a real application, you're typically going to have to hook multiple system calls and then integrate that knowledge into a coherent view of what's going on. And now you're sad again, right? You're sad, right? Because there's all this great data in there that you could do something with if you could just figure out programmatically how to get at what you want, right? But maybe, coding's not your thing, or this whole, notion of performance tuning is new to you. And you absolutely can learn to do this stuff on your own. But the good news is that there is this whole ecosystem of projects, both open source and commercial projects, that are growing up around this eBPF data source and already doing very powerful stuff, right? So rather than you having to reinvent the wheel, you might be able to find, a project that does for what you wanted to do. And so that's why we brought Jon along. Because Jon and I've been sort of doing technical advisory work for Spyderbat, company that Jon works for. And they have this really interesting Linux monitoring solution that eats eBPF data. And so I wanted Jon to show you all what a mature product that's based on eBPF can do with all this data. It's really, really freaking cool. So Jon, I'm going to turn the screen over to you.
Cool. Thank you. Thank you, Hal. Thanks very much. Let me share my screen real quick. Okay. Can you see my screen okay?
Looks good to me.
Great. So, yeah, my name's Jon Reeve. I run product management at a company called Spyderbat, and our focus is on visibility and securing your cloud container Linux systems. So we started with Linux, we started with cloud, and as folks are moving workloads there, running workloads there, and from the get-go, we knew eBPF was going to be an important technology for us. And so, as Hal showed you, eBPF is very powerful. You can get all kinds of things from it. But
hey, Jon.
Yeah. Hi.
Can you go ahead and zoom in on this one? I think the other ones are zoomed in, but this one.
Yeah, sure. I'll zoom in a little bit.
And the words on the left and right.
Sure. How's that? A little better?
A little bit more.
Okay. How's that?
The words on the left and right, I think, are good. Perfect.
That better?
I know it's going to be a little awkward for you, but
it's all right. No, keep me honest here. So, again, we started, the founders of Spyderbat, I'm just going to zoom out real quick, but the founders of Spyderbat, worked in operation centers. They founded a couple of security companies, and they had really observed analysts trying to put together a picture of what's happening in their environments. And they're like, well, how can we do a better job of this? In other words, how can we create this kind of picture that tells the analyst exactly what's happening in our environment, what's connected to what, so that the operators don't have to trawl through Audit D, trawl through logs and other mechanisms that Hal was talking to. How can we kind of surface this to you? And so eBPF is an important component of that in terms of it allows us to get this primary data that Hal was talking about off the box. So what are the important system calls being made? What are the important connections coming in and out of the box and so forth? And so we actually install a very lightweight agent. It taps into that eBPF information. And again, we're capturing very specific eBPF information so that we can build this targeted picture for operators and analysts of what's happening on and between their Linux systems. What you're looking at here, real quick, is basically a connected graph. But the S node here is a system node. Basically, we've installed our agent on a couple of cloud systems here. One on my jump box, one on my configuration server. And then the way to read this is kind of from top to bottom and left to right. So we're collecting this, shipping this eBPF information off of the server in a very lightweight way back to our back end. And again, continually putting this picture, this living map of activity together for you so you can see what's happening on your systems. That system booted, it started the system D process that ran under the permissions of root. So that's the effective user here. That kicked off an SSH process. That kicked off another SSH child. And just to explain what we're looking at here, basically there's a user that logged into this box as user Jim. That's the effective user that logged in here, and then started a bash shell. And then, we can see exactly what Jim did in this bash shell. Again, we're taking this eBPF system call information, piecing it together in a graph or causally related. So we know that Jim was the one that logged in this case. Jim started a bash shell. And then we know exactly what Jim did in the bash shell. So, Jim, you can see a little bit more information down here. Jim did an ls command, enumerated the system, seeing what version of Linux he's running in this case, just get the date. And then Jim moved over to another server. This is actually a real scenario here that many of our customers have experienced where, somebody logs into a jump box, as their user account, and then they move around in their environment. In this example, for example, they're SSHing over to a different box, the configuration server. They're going to make a change in their environment as a shared account. So now they're the Amazon EC2 user on an AWS Linux box. And now they're logged in as the EC2 user. They started a bash shell there. They ran an ID command. They escalated. They did a sudo to basically make themselves root. They got that bash shell. And in this particular scenario, somebody accidentally made it, never happens, of course, but somebody accidentally made a configuration mistake. Somebody deleted a cluster, for example, in our Kubernetes environment. And yes, if you had Audit D configured the right way, you could certainly see some of those commands. You might even see that the authenticated user was an EC2 user, but certainly putting that chain of activity together and certainly putting it together across different instances in our cloud environment is a really difficult thing to do. So in this case, some of our customers, for example, struggle like, well, who's actually using these shared accounts on these machines? Who actually did this, from an audit perspective, who actually deleted this cluster? And now I can get a picture. I can get attribution here. So I know that, yes, somebody logged in as EC2 user, but if I trace back through this graph, I know that it's actually Jim. And so it's very powerful in terms of putting together those raw components that this powerful eBPF technology allows us, but then stitching it together into this living graph. Now, on top of that graph that we're building all the time in the environment, we also layer on security context or security signals. So it's just a simple one, but somebody escalated privileges to root here, right? And we've layered on a little flag on top of that graph. And you'll see how we use that in the next scenario. But basically that allows, together with the graph of activity that's happening, these security signals allow us to build a trace, a very targeted trace, or if you like, a subset of this graph that we need to surface up to our operators and our analysts, whether that be to surface an operations issue, a security issue that's happening, and so forth. So let's look at another little example here. So many of you are familiar with Log4j. It's very, very near and dear to our hearts. And I know many of us had to work, I'll say the nightmare before Christmas, but right before, before around that time, kind of working on this 0 day that came out around the log4j package. And what I'm actually going to do here is just kind of show you this attack kind of. Oops, I'm going to go back a little bit as it unfolds. I'm going to rewind a second. So what this is showing us, basically, we've got a vulnerable web server that we've set up. It's running Tomcat. You can see Java kicked off under the Tomcat service account here. It's kicked off a Java process, and we're going to kind of play through, what happens when somebody, we've installed our agent on here that's retrieving that eBPF information. What happens when somebody attacks this with a log4j exploit? So the first thing, I've got an inbound connection, a web connection coming from this IP address to port 8080. And basically what's happening here is somebody's injecting that the string here to basically trigger an LDAP query back out to their system. They've injected this string, so that we're going to basically go and retrieve, do the LDAP thing that log4j does, and then go and retrieve a malicious Java class in this case. Clicking on the next step here, basically that again, you can see a connection going out from that Java process. Again, we're tying we're taking this eBPF information and not only looking at the chain of system calls that happens, but also the connections that are tied to the specific processes, whether they're outbound or inbound, that cause activity to happen on the system. In this case, a connection goes out to the LDAP port here. And then we get another connection go out. And basically what's happening here is this Java process is now going out to fetch. We can see a little bit more details about all the parameters of the process that are running here. And we can get a lot more information around the working directory, environment variables, all that good stuff. But this Java process has basically gone out and retrieved a Java class now. It's going to basically do remote code execution. It's going to execute in that process. First thing that happens here, that Java code gets executed and it goes out and retrieves a package. And this time from a different endpoint. It changes the file on that package. Okay, so it changes the permissions to make it execute. It executes that file. And again, we have the complete chain or causal chain of activity that's happening on the system here. Now there's a bash shell. And you'll notice that bash shell actually has a reverse connection back out. So now basically the attacker here has got a reverse shell on our system. And again, you can see these little red dots context in and of themselves. These red dots are perhaps, not terribly interesting, but when they're combined together in a causal trace of activity, we know that something, really nefarious is happening here. And so I'm showing you this system and unfolding this attack after it's happened, but Spyderbat's also monitoring this live. So we're creating these so-called traces from activity as it's happening in real time and scoring those traces. And I'll show you a little bit what that looks like in a second. So the attacker now has persistence on the box here. They did a reverse shell. They're actually enumerating the system a little bit more. And basically, you can see here they cat a text file here. Basically, through that they retrieve a password, and then a little bit time later. And again, we're insensitive to time, so this could be 24 hours later. This could be a week later. This could even be a month later potentially. They escalate their privileges, and now they're under a different account here. The server admin. They're running additional enumeration. They curl and get a different package. Again, we made this a little bit friendly for the sake of this example. They've got a crypto miner package here. They execute that package, and we keep going. They make that executable, and then they run it. And so now we've got a complete story, or trace, as we call it, of this attack, both as it's unfolding. Again, we were recording this in real time, but also an after the fact record. And again, we can go back quite long periods of time for you to understand what's happening here. Okay, so we're building this living map of activity on and between our cloud systems, our Linux systems, our containers. How does an analyst actually get into this? So again, we're building these traces, and these traces, that's a little bit big, but these traces are scored live. So as this activity is happening, as we see those flags or that security context happening on those traces, we're continually scoring them and bubbling them up. So maybe there's a low-level trace we've started, administrators logged in, they're doing some activity, but there's a couple of flags on there, but it's a pretty low score. As that trace continues to unfold, as that causal activity continues to unfold, either on a single system or across systems, we continue to elevate that score and surface the higher score traces to the analyst. And then at any point in time, an analyst can click on one of those, start an investigation, and get right into the picture we just saw. So they can get straight to the subset of this graph, if you like, to really understand what's happening, and take action and maybe shut this thing down if needed. I want to give one more example because, again, we're very much focused on cloud systems, container systems. I'll zoom in a little bit more again. And I want to give an example in a Kubernetes cluster. So, because one of the drawbacks, for example, from Audit D is that it does not have container context. It's not container aware today. And so using eBPF, we can understand containers as well as regular Linux systems in Spyderbat. So in this case, we've got actually a managed Kubernetes cluster, happens to be on AWS, and we've got an inbound connection to the kubelet on our Kubernetes node. This is actually a Kubernetes exec. Somebody's done a Kubernetes exec into our cluster, and that's basically done a process chain of activity that leads us to a shell inside our container. So now somebody's got a shell inside our container. We've actually colored this trace or this graph by the container context. So the blue nodes here are the processes running on the underlying VM or bare metal node. The green processes here are the activity that's actually running inside our container. And so somebody's done a kube control exec. We can see we've put relative time on here, so we can kind of see when somebody does something. So a minute later inside of that bash shell, somebody performs a who am I command. 22 seconds after that, they perform a curl command. Basically, they're trying to make sure they have outbound connectivity from inside that container. Next, they go ahead and do a number of commands here. So they make a directory, they mount something here. You can see that they're mounting actually a C group here. And you can see these series of commands happen very quickly, one after another. So within 11 milliseconds. So they're either copy and pasting something or running something in a shell, etc. And basically what happened in here is they're running a sequence inside of our container to launch a container escape. So the last step here is basically escaping the container. So now, if we go to the next step of this trace, right up here, basically they've escaped the container and now have a bash shell on the actual underlying VM or bare metal node or whatever, the container's running on here. So you can see the full set of activity from inception. So, a lot of systems might tell you something happened at the end of the chain, like something bad happened. But the problem is, how did they get there in the first place? How did they get in? Did they leave 5 backdoors before they got in? And this gives you the causal sequence or the story, essentially from the inception. And again, this is also happening in real time. So it allows you to get one of these traces very quickly from the dashboard. And if it has a high score, intercept it. But in general, just understand, visibility wise, observability wise, what's happening. Is it bad? Do I need to intercept it very quickly? And again, eBPF as a tool is very powerful. But as you saw from Hal, there's just tons of different system calls you can get. The key here is that we've started with this picture. Like, how do we present this to operators, and what are the key pieces of information we need to get in order to build this connection, build this picture? And so it's very efficient. Again, like in terms of we're just grabbing the data we need, we're offloading it, we're not processing it on the server or the endpoint, and putting it back to our back end to piece this picture together.
And then, the other interesting thing, which John doesn't have time to go into, is it's historical too, right? So John mentioned that they're sort of independent of time. But the other thing is, suppose you find a new TTP that isn't necessarily flagged by Spyderbat, you can then go back and look historically through the data that's collected for other systems where that TTP has occurred, and begin to do scoping on other systems that might have been compromised as well. So it's freaking cool. Is all I can say about this. And the more you play with it, the more you realize, oh my God, there's so much stuff to do here.
Yeah, not to go too marketing on it, but we kind of liken it to a DVR. So it's kind of happening in real time, but you got this kind of time slider. Like, hey, what was happening last week? What was happening last month? And like, I've seen a TTP. What other TTPs have happened that look like this, right? That I can go explore on this DVR. So that is a key point. Thank you, Hal.
Okay, so this is what you can do with eBPF if you start with presentation, right? Like what do people need to look at to do their jobs, right? And so you can imagine all these like amazingly cool things you can do, right? But we wanted to give people time to ask questions, so hit us up.
Sounds like it's my cue. All right. John, thanks. What is the retention capability?
Yeah. By default, we go back kind of 3 months. It's configurable. So it does go back a long period of time. And again, part of that, because we're being very efficient in terms of how we collect those systems calls and bring it to our back end. But that's really important because, with things like supply chain attacks and that kind of stuff, like, again, people leaving wait periods, like, we need that length of time to be able to see what's happening. So 3 months by default, short answer, but it's configurable and you can extend it beyond that even.
Yeah. So I don't know if we need this follow-on question, but how hard to configure that retention across systems?
Yeah. That's not super hard. That's something we can do today. Again, our customers get 3 months, by default, but it's pretty easy to change that. And again, that data is stored on our back end. So, we're a SaaS provider. So that's not something that should impact you as a customer.
Someone wants to know if we should have a Spyderbat cert in the Antisyphon.
That
would be awesome. That's a great idea.
We should set up something on the range, certainly. So by the way, speaking of setting stuff up, there's a free tier, right? So if you want, you can go to the Spyderbat's website today, sign up for an account, and put this on 5 nodes for free. Start using it right now.
Yeah, pretty much they wouldn't be here today if there wasn't a free option. That's the way we roll here.
And there's also a little CTF on the Spyderbat website. So it's got 10 or 11 challenges that you can work through to kind of get a handle on the interface. And I did it. It was a lot of fun.
Yeah, so just to say, we did what I just showed you. We put the agent on some boxes. We hacked them, various scenarios, and we recorded it in this DVR. And now you can kind of replay it and play a quiz and look at what some real attacks look like on your Linux systems.
I always like when there's a CTF or something involved to use the tool that way, because it's like almost gamified. Like, I want to see if I can use it. What is eBPF's relationship to Strauss?
S-Trace.
S-Trace. I just showed my... that's fine.
So S-Trace is the Linux system call tracer command line tool. It's basically sitting there and logging every system call a process does. It's not using eBPF. S-Trace predates eBPF by a significant amount, but they're basically using the same kinds of data. They're sitting there on system call entry and exit points and logging data. It's just that eBPF is the sort of programmatic way of linking that into your own code.
What load is put on the endpoint?
Yeah, I'll take that. So it's pretty low. I mean, it's, it depends on the workload, but generally pretty low because, again, we're trying to grab this subset of eBPF information and ship it to our backend. So we're not doing the processing actually on the server. We're basically sending over the network to our backend where we process that and put together this map. You're talking 1% to 2% CPU, typically 100 megs memory, and pretty low bandwidth, right? Because it turns out that, again, when you actually pretty targeted in what you want to collect from eBPF, it also compresses very highly. And so, hundreds of kilobits back to the stream, back to our backend. So it's pretty low impact relative to probably what and that's important because you're running important stuff on your servers here.
Does eBPF require new libraries to be linked into your executables?
No, because it's happening at the OS layer. So it's independent of user space. That's how we get mandatory monitoring. And also to the question we were answering earlier about performance, remember that most of the filtering and selection that eBPF is doing is happening in this little virtual machine in the kernel. So you're only exporting data to user space that your program says that it wants, and that's what makes it much more efficient, right?
Why does Spyderbat work? How does Spyderbat work with on-prem non-container virtual machines or physical nodes? How does it work?
No, absolutely. It's all good. So if you're running Linux, a modern version of Linux that supports eBPF, so for example, like Red Hat 7.6 or later, or Ubuntu 18, as long as you're running a Linux system that supports eBPF, we're good. So we can install on your on-prem server, we can install on your cloud server. And again, that we roll all that back up to our SaaS backend. So, hybrid, multi-cloud, on-prem, that's all great data source for us.
Let's see if this dovetails good. It says, hi all. Question 1. I know this is supposed to be light, but for multiple or very many Linux systems, should you have a dedicated internet connection VPN for the traffic?
So can certainly do that. You can certainly have, a VLAN or something that, does the traffic. Again, the traffic is pretty lightweight in terms of, for Spyderbat specifically, like, getting this data off the agents, off the servers. So we typically don't need to do that. So again, it's really not adding a lot of network traffic to your setup typically.
How does this compare to Sysmon for Linux?
So Sysmon for Linux, it's just, again, it's the data vomit problem, right? You've got all this stuff spewing out and it's great data, but you have to somehow, munge through it and get to the stuff that you need to reconstruct what happened. The goal for Spyderbat was to start from the opposite direction. It's like, here's what you need to reconstruct what happened. Now let us, push up the data that you need in order to do that. So, Sysmon for Linux is awesome, right? But it's just a lot of raw data that you then have to process efficiently in some way.
And so generally what happens is we get asked more questions and we can answer live. Sometimes, like today is one of those days. So what I'll do is I'll get the questions over to John and Hal. And if you want to follow up with a secondary webcast or something in the future, or a blog post or something that can go along with some of these questions. But I have one last one for today. Is Spyderbat hosted in an infrastructure that is FedRAMPed?
Good question. We're not FedRAMP today. I think it's something we'll look at from a roadmap perspective. We are running on a backend cloud provider that does have a lot of those certs, depending on basically a major cloud provider that has all of that stuff. But for our product itself, we're not FedRAMP today, but certainly something we're looking at as we go forward.
Well, everybody, thank you so much for joining us today. I always like to close with Hal. Any last words?
No, don't be afraid of eBPF. It's really, I think, an important technology. It's going to subsume a lot of things in Linux that we've been doing from a security perspective, including NetFilter and SE Linux. So I would say start poking at it and start getting used to it, because I think it's going to become where Linux is going from a security story in the future.
John, any final words for us today?
No, I thank everyone. Thank you all here for joining today. I kind of agree with Hal. There's a question in here, hey, what about, not just detecting stuff, but blocking stuff, and directionally, EBF's going there too, right? So not just as Hal was mentioning, like being able to observe what's happening, but also be able to, in more modern versions of the kernel, be able to intercept those calls and stop them. So, I guess watch this space.
Yeah. And we'd like to thank most of you who are here today because you have taken an Antisyphon training class in the past, and that's how you got on the mailing list in the first place. And so thank you so much for taking a class with us. We hope you take another one at some point in the future whenever you need us. And in the meantime, keep showing up for the Anti-cast. We'll keep doing this on Tuesdays and Wednesdays, live streams on Twitch and YouTube. And then on Thursdays, we'll do our Zoom webcast like normal. Thanks, everybody. We'll see you next time. Bye-bye. Ryan, kill it. Kill it with fire, my friend. Kill it.